moving on, there's another property of partial derivatives known as the commutative property. And so this property has to deal with second derivatives. And so essentially with this property, let's say that we had dx dy constant z, and then we took the derivative of it, of this, with respect to z at constant y. Okay? What the commutative property tells us is that we could switch out the order of derivatives here. And so essentially, this sequence of derivatives we have on the left-hand side, the commutative property tells us that it's equivalent to just saying that we took the derivative of dx dz at constant y. We would be taking the derivative of this with respect to y at constant z. So here, if we took the derivative of y first and then the derivative of z, commutative property tells us that's equivalent to taking the derivative of z first and then taking the derivative of y. Or otherwise, both of these are equal to the second derivative of x dy dz. Okay? So commutative property just tells us that the order of our second derivatives doesn't matter. Okay? All right. Another useful property of partial derivatives is the expansion rule. All right, and so this is if we had dx, so x, the partial derivative of x, with respect to some variable k at constant L. All right. We could rewrite this derivative and expand it out like this. So dx dk at constant L is equal to dx dy at constant z, dy dk constant L, plus dx dz constant y, dz dk constant L. And the idea here is essentially we're just expanding it out so that, multiplying it by 1 essentially. You're multiplying it by like a dy over dy and a dz over dz. Okay? So that's what the expansion rule tells us. And then there's a special case of the expansion rule called the chain rule, which you've seen before. But in this case, what we're doing is we're letting L equal z. All right, so L here is going to be equal to z. All right, and so if we rewrite the expansion rule following this new constraint, what we have is dx dk constant z is equal to dx dy constant z at dy dk constant z plus dx dz constant y and then dz dk at constant z. Okay? But once again, we have dz dk at constant z. That is equal to 0 because we're taking the derivative of a constant. And so what we're left with is dx dk constant z is equal to dx dy constant z dy dk at constant z. Okay? All right, and this identity is useful. I'll just say useful for adding in a new variable into your partial derivative. In any case, I want to stress that so far I've just only focused on math, right? I haven't mentioned anything about physics. This is just how partial derivatives work. These are different properties of partial derivatives. And so here I just use x, y, z, k, and l. But in thermodynamics, and especially the chemical engineering version of thermodynamics, our variables are typically internal energy, entropy, enthalpy, pressure, volume, and temperature, right? So instead of x, y, z, we would use some of those, okay? And in this chapter, we're actually going to introduce a couple of more variables. So we will also introduce something we call the Helmholtz energy. And so that's abbreviated as A or F. And we'll also introduce something known as the Gibbs energy, which is abbreviated as G. All right. And so the reason I wanted to show you all this math, so I just showed you pure math right now, is because we will use these properties, or we'll describe all of our variables in terms of partial derivatives. So we will use these properties of partial derivatives to rewrite our thermodynamic variables, or recast them, in terms of things that we could actually measure. So recast our thermovariables in terms of measurable properties. And so that's at least the motivation for why we went over all this math.